In this video, we're going to look at finding a numerical solution to a first-order differential equation. Now, this can occur when we have a derivative is equal to some expression and we can't find a simple closed answer to the integration. It's not easily integrable to give us a closed exact answer by any of the known standard methods. So we can resort to a numerical solution, an approximate solution. Okay, and we can make that solution as accurate as we want to, and I'll show you that shortly. So it's possible to generate a set of points that are close to the points that lie on the actual solution curve, but how close is up to us, again, is our choice. Now, let's just say y equals f of x here is the solution. It's the exact solution, okay? Here's the actual solution to our problem. So let me motivate an argument and use this as to help generate a method that we can use for when we can't find f of x by integration. Okay, now we pick a point here, x0, y0. Now at this point, we draw a tangent to the curve. It touches the curve at that point only. It's a straight line tangent. Okay, and the gradient of the tangent is equal to the gradient of the curve at that point. Okay, that's all we need. So the gradient of the tangent is equal to the gradient of the curve at that one point, and that point is x0, y0. Okay, now at x0, we're going to draw in a right angle triangle. Okay, so we're going to draw in a right angle triangle here. I better get my pen up. And the base here is going to lie between x0, x1, and the rise here will go from y0 to y1. Okay, so this distance here, x1 minus x0, we call that h. That'll be our step length. Okay, all right, now the gradient of that tangent is the rise, y1 minus y0, divided by the run, which is h. Okay, and that's equal to the gradient of the curve at the point x0. So it's equal to f dash of x0, evaluated at x0. Okay, a little bit of algebra says that y1 minus y0 is equal to h times f dash of x0. And if we were to take the y0 on the other side, we'll have y1 is equal to y0 plus h times f dash of x0. We're going to use this rule here in a general form to help us generate these points y1, y2, y3, which step us up the curve. Okay, we're always going to start at some point x0, y0. All right, and then we're going to step up and generate these points. Now these points are close to, but not on the actual solution, but close to. They're a good approximation to it. And the way to make these points a better approximation is to keep the step length h smaller, shorter. If we make it shorter, these points will lie increasingly closer to the curve. If we make it shorter, the shorter we make it, the closer to the curve we get. Okay, so that means we need more iterations. Okay, now the process is, you can see that if we step along h units, the next step here will be x1 to x2. Okay, so that x2 will be x1 plus h. Okay, x2 will be x1 plus h. Okay, and in general, xi plus 1 will be xi plus h. See how this xi is 1 before this one, plus h added on. In a similar way, the y's are going to work this way. yi plus 1 will be equal to the y before plus h times f dash of xi. Okay, so this and this will match together. xi, yi will match together. They will help us generate the next y, I plus 1. All right. Now the trick, this is an approximate method that yields a curve like this, but it's approximate. But we can make it more accurate by making h smaller and smaller. Okay, let's have a look at an example. And here's our example here. It's going to be dy dx, first order, is equal to 2x. Okay, initial boundary condition, y of x0 is equal to 1, y0. Okay, now the solution to this is y equals x squared. You can just see that y equals x squared, dy dx is 2x. Okay, so this is just as a demonstration of the method. I mean, y equals x squared means that when the answers we generate from here can be compared with the actual solution y equals x squared itself to see how close we are. All right, now here we go. I is 0, so this one is x0. Okay, this is y0. Okay, we're told that. We've given that before. And here, f dash of xi, this is f dash of x0. Okay, x0 is 1. Put 1 in there. 2 ones are 2. So, all right. Now, this will be x1. This will be y1. All right. And this here will be f dash x1. Okay, now x1 is 2, put 2 in there, 2 ones are 4, so f dash of x1 is 4, okay, y1 is 3. Now, what we're trying to do, and this will be x2, y2, all right. Now, to generate, we've got to generate y1, okay, I want to generate y1, so I'm going to have y1 here, will be y0 plus h, which is 1, times f dash x0. Okay, so y0 is 1, plus here 1 times f dash of x0. x0 is 1, put that, so that's 2. So y1 gives me 3. All right. If I now want to develop y2, then I'm going to need here y1 plus h is 1 times f dash x1. Okay, now y1 is 3 plus 1 times f dash of x1. x1 is 2, so I have 2 by 2 is 4, and so 3 plus 4 is 7. Okay, y2 is 7. And then this way I keep going down. I'm going to have x3 here, y3. Okay, this was f dash x2. Now x2 was 3, put 3 in there, 2 3s are 6, so that adds up. All right, this is f dash of x3. Okay, now f dash of x3 is 4, 2 4s are 8, so that works out. Okay, now I've got y2 is 7, so that's checked. y1 is 3, that works. Let me get y3 here. So y3 will be y2 plus 1, the step height is 1, times f dash of x2. So y2, what do we get for y2 is 7 plus f dash of x2. F dash of x2 is 6. Okay, so 1 times 6 for the step height. And that's going to give us 13. Okay, and that's what we've got. Okay, so what we do now is we now plot y0, x0, y0, x1, y1. The next pair is x2, y2. The next pair is x3, y3. The rest are provided down here. So this is x4, y4, okay, f dash of x4, and we just keep going down like this. Okay, so xi is 1, 2, that's these 3, 4, 5, 6, 7 down here. The numerical solution values here are 1, 3, 7, 13, 21, 31. Okay, now if you look at the actual solution values, remember the actual solution in this case, the actual solution was y equals x squared. Now 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49. So the numerical values here, the approximate values, 1 and 1, well that's close, 3 and 4 are close, 7 and 9 not too bad, 13 and 16 a bit off, 21, 25 a bit off, 31, 36 a bit off, 43, 49 a bit off, okay? But we could have improved these by making h smaller. Okay, so working these through down the bottom here, y1 is y0 plus h times f of x0, and so on, y2, y through, just been through all this, y4, and so on. Okay, because if you remember, f dash of x for us was 2x. Okay, so 2 times 1, 2 times 2, 2 times 3, 2 times 4, okay, 2 times 5, and so on for each of these x values. All right, you can see now, depending on the step length, if you can reduce it in size, you'll make the problem more accurate. We will get closer. And I suggest you try this problem here, but instead of using a step length of 1, try using a half, or go a bit further. Try, say, 0.2. It'll take longer to generate the points, but you should start to see that you get closer. It might be a worthwhile exercise. Just extend this question by doing that.